All right, guys, this is Unit 2, Quiz 3 study guide. I'm going to be doing the even problems. Once again, you have the odd problems if you want to practice a little more with the answers provided at the end of the document. All right, so we got to recognize these types of integrals. These forms where you have these fractions so far, they've been the arc trig function ones. And so let's go ahead and begin. First of all, notice the form. So we are dealing with an arc sine situation. Okay, with arc sine, basically, what we're going to do is we're going to take the square root of that number, the square root of that number, and that's the integral. Okay, so it's just a matter of remembering the formula. Let's go ahead and take a look at another one here. So this is another one that's another arc inverse trig function. It's going to be the arctan function, which looks something like this. You have a fraction in the front, a fraction in the parentheses, and a plus c. But before we can get there, we have to recognize there's a little bit of a problem here. It's the power down here needs to be a square, not a 10. And so what we do is we're going to begin by rewriting this. So that what's in the parentheses there will give us something equivalent to this once we square it. And that would be 4x to the 5th. So 4x to the 5th squared is the same thing as 16x to the 10th, but now I've rewritten it as a square. And that way it fits the arctangent pattern. Now, when we have to do that, we have to turn this into a u-sub problem. So my u would be 4x to the 5th. My derivative with respect to x would be 20x to the 4th. And then we get the dx by itself. Then we're going to go and do our u-substitution. The 20x to the 4th is going to stay there. The 16 is going to stay there. But we're going to replace this now with u squared, and we're going to replace the dx, which I didn't write, but there it is. We're going to replace the dx with what it equals, du over 20x to the 4th, and then these cancel. And so now I have 1 over 16 plus u squared du, and now that's a more classic looking arctangent problem. So what we do is we take the square root of this number. That gives us the denominator, both outside and inside. We take the square root of this number, and that gives us this number here. The top will just be a 1 in this case. And, of course, we want to go one more step now and replace the u with what u is equal to. U is equal to 4x to the 5th. Now, technically, we could reduce this. I'm not sure if my software is going to take that step or not, but it's not a big deal if you do or don't right now. I'd say just make sure you know that you can, but it's not necessary. All right, so sometimes you have to do u-sub with these types of problems if they don't fit the pattern appropriately. Now, this one that we're looking at is not going to be an arc trig function integral. How do I know that? Well, there's two things that kind of tip me off. First of all, we need perfect squares here. Now, I could rewrite the x to the 4th as a perfect square, but I can't rewrite a 5 as a perfect square. And I also can't rewrite the 2 as a perfect square. And when you're dealing with arc trig functions, those need to be perfect squares. But here's another hint. The fact that this power is 1 more than this one, that usually indicates we're going to do a u-sub problem where the u is the denominator. Okay, so this one is not an arc trig function, and the indicators were we don't have perfect squares, but also this power is 1 more than this. And in that case, we're just going to make u equal to the denominator. Now we'll go ahead and solve it, or work through it, I should say. The negative is going to stay there. The 40x to the 3rd is going to stay there. The entire denominator we decided was u, and the dx was du over 20x cubed. Now the x cubes go away, and 20 goes into 40 twice. So rewriting this in a little bit of a simpler format, I've got negative 2 over u du. Right? Now that, if I just take this negative 2 and I pull it out of the integral there, you guys can maybe see a little bit more clearly what we're dealing with here is an ln integral. So when I integrate this, I get ln of the absolute value of u. So that's how you integrate that one. We get negative 2 ln, and we'll put the stuff back in there. We have 5x to the 4th plus 2 plus c. This is a fine answer, but I do want you guys to be aware that 5x to the 4th, notice that this is plus, and this is always positive. So if you take a positive number and you add a positive to it, guess what? It's always positive. And if it's always positive, when you take the absolute value of it, it stays the same. So another way that this could be written is you could just use parentheses instead. So don't be surprised if maybe you see that on the quiz. But you got to be careful. You're only allowed to do that if this is always positive on the inside. Let's go ahead and take a look at number 8. This is an exponential function, and when we do these, the u is almost always, not always, but almost always just going to be the exponent. So my u is 4x to the 5th minus 3. Then we take the derivative and get the dx by itself. Now some of you guys might be wondering, well, how would you know when it's not, when the u is not just the exponent? Well, it's kind of tricky. There's two ways you can identify what your u is. It's the inside function, or it's the thing whose derivative is somewhere in the problem. So you kind of just have to get really used to u sub in order to identify that kind of stuff. Practice, 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 in other words. But there's that. So now we're ready for it. The 20x to the 4th is going to stay for now. Then we have e, but we're going to replace the entire exponent with a u. And then we're going to replace the dx with du over 20x to the 4. And as you can see, the 20x to the 4s go away. And the integral of e to the u is simply e to the u. And we replace the u with what u equals. And that's the end of that one. Okay, so whenever you have a quadratic trinomial in the denominator like that, we're going to start by rewriting the denominator by doing something called completing the square. Completing the square means we're going to add a new number after the second term, and then we're going to subtract that same number after the last term. The new number can be found by taking half of the middle number first and then squaring it, which is 16. And that's what's going to go there. You also put it there. Now this creates what's known as a perfect square trinomial. And when you factor those, they always look like this. The only thing that looks different is you take half of this middle number here, which is negative 4. Then we're going to combine these together. 17 take away 16 is 1. And that's what I'm going to start by doing, is replacing my denominator there with x minus 4 squared plus 1. The next thing we're going to do is we're going to do some u sub. So the u is the inside part. The derivative of u with respect to x is 1. And so when you get the dx by itself, you actually find out that du is simply equal to dx. Doing our u substitution then, I'm going to replace this with u. I'm going to replace this with du. And my 9, typically I would have left it there, but I'm going to pull it out to the front. Now, the reason I did that is because now what we're looking at here is a classic arc-tangent problem. And that 9 is still in the front there. So we take the square root of this number, and that's what goes here. We take the square root of that number, and that's what goes in the denominator. And there's always a 1 here. And so simplifying this, I have 9 arctangent, and we don't really need the denominator of 1, but we should replace the u with what u is equal to, and that's x minus 4. Okay, so there's that particular integral. All right, so number 12, we're going to go ahead and do a definite integral here. So this one is going to be an ln. Anytime you have an x to the first power on the bottom and then no x's on the top, that's probably going to be a ln type of problem there. So we're going to start off with some u substitution. My u would be the denominator. Take the derivative of that. Get the dx by itself. Go ahead and do our u substitution. I'm going to take that 5. Matter of fact, I'm going to take the negative 5 and I'm going to move that out to the front. I'm going to replace the denominator with u, and I'm going to replace the dx with du over 2. And we also need to change these numbers here. Since we're doing u substitution with a definite integral, you have to change the limits. So the top number right now is 0, but if I plug it in here, that will tell me what the corresponding u value would be, and that's negative 2. And then the bottom number was negative 2, but if I plug it in here, I get negative 6. So now my bottom number is negative 6. Now, I'm also going to take this negative 2 here and I'm going to slide it out to the front, and that would look like this. Okay, so now that we have the constants pulled out to the front and the limits changed, we're ready to integrate. The integral of 1 over u is ln of the absolute value of whatever the denominator was. So now we're going to have negative 5 over 2 ln of the absolute value of negative 2 minus negative 5 over 2 ln of the absolute value of negative 6. So you just plug them in and subtract them, right? The absolute value here is just going to be a positive 2. Here, these two double negatives are going to become a positive. And then the absolute value of negative 6 there is going to be 6. Now, I would be okay with this answer personally, but I just know that how my software is going to write it is they're going to take these denominators here, and they're just going to put the whole thing under that denominator there like that. I'm not too sure why they want to write it like that. You can write it that way, just I don't see why. There's other things we could do that are better, honestly, but this is what it'll look like on the answers, just so you guys know. All right, so there's that. And do be aware that while I'm aware you guys can do this on a calculator, this is going to be a non-calculator test, so I do want you guys to be able to do these things by hand. Okay, let's go ahead and take a look at yet another one here. All right, number 14. So for this one, we can see that this fits an arc-sine pattern. The square root of this number goes on top. The square root of this number goes on the bottom. So that's the integration there. Now we'll go ahead and plug these things in. Arc-sine of radical 2 minus arc sine of, oh, I'm sorry, radical 2 over 2. If you plug in that, you still have the denominator of 2. And then when we plug in the 1, we get 1 over 2. Okay? Now I don't mind if you guys want to use notes. If you want to use notes, then you can use the trig reference sheet that I've given you. And what you would look at on there is you would just look for where sine is equal to radical 2 over 2, and you would find the angle that goes with it. But you do need to remember that for arc sine, we only take numbers from this half of the circle, and we have to remember that numbers that are below this horizontal line here are going to be the negative versions of the angles above them. So just keep those things in mind. And these numbers will not be on the reference sheet. You would just have to have that memorized there. Now, as for me, though, I like to just figure it out, and I don't want to use notes. So I know that on a unit circle, first of all, sine represents the y value. So I'm looking for where the y value is a positive radical 2 over 2. I also know that with arc sine, we're only looking at this side of the circle. So it's positive on the top half. So radical 2 over 2 is the number right here in the middle. And I know that that angle is pi over 4. Next, I have this one here. Once again, we're looking for the y value. And I want to find where the y value equals 1/2. And that's down here. And I know that that angle is pi over 6. So I have pi over 4 minus pi over 6. So I would need to get a common denominator there. I think the common denominator is 24 if I'm not mistaken. No, actually 12. We can go smaller than that. So I'll multiply the top and the bottom of this one by 3, the top and the bottom of this one by 2, and that will give us a common denominator. So we have 3 pi over 12 minus 2 pi over 12, and then 3 pi minus 2 pi is 1 pi over 12. Once again, this is going to be a non-calculator based question, and so you're going to need to know how to do this without a calculator. You may use your notes, of course, if you wish. It's still capture graded a B, but if you want to use your trig notes, you're welcome to do that. Otherwise, you could try to figure it out like I did here. Okay. All right, guys, and here's the FRQ portion of our study guide. Now, for these guys, they're all going to be some kind of a U-sub, but with a table. So the U is the inside function there, so that would be the G function. So U equals G of x. The derivative of U with respect to x is G prime of x. And then if we get dx by itself, we get du over G prime. So if we go ahead and do our U substitution, we have f prime of U. Then we have our G prime of x there. And then we replace the dx with du over G prime of x. And these are going to cancel out. But before I go any further, we also need to change our limits. So if I want to find out what the limits are, you're going to plug them in here. So I have u is equal to g of 1. And according to my table, g of 1 is negative 1. So the top limit is going to be negative 1. And then I'm also going to plug in the bottom limit here. So u is equal to g of 0. And g of 0 is 2. I've got a 2 there. So I'm going to go ahead and make some more writing space for myself here. And we're pretty much ready to solve this at this point. The U substitution is all over. So now I've got an integral that goes from 2 on the bottom to negative 1 on the top. And sometimes when you do the U sub, they end up backwards like that, where the bigger one's on the bottom, but it really doesn't matter. That's okay. It's not a problem. But let's go ahead and do it. So now we integrate. The integral of f prime is f. Then we plug in. And I'll continue my work up here. f of -1 is 5, and f of 2 is -1. And so we have 5 minus a -1, or in other words, 6 is my final answer. So we're doing U substitution using a table. Let's take a look at a second problem. All right, just another type of U substitution. So in this one, my U would be the 2x there. So the derivative of U with respect to x is 2. Getting the dx by itself, we have that. And then we'll rewrite our integral. So we have g prime of u, and then replacing the dx, we'll have du over 2. We also want to change our limits, so I'm going to plug the 1 in here. So if I do that, I get u equals 2 times 1, which is 2. So the top number becomes 2. To find the new bottom one, we plug in the old bottom number, 0. So u is equal to 2 times 0, which is 0. That goes there. I'm going to go ahead and take this 2 out that's on the bottom. You've got to keep in mind that since it's on the bottom, when you take it out, it's a half because it's in the denominator, right? Now we integrate the g prime and we get g. And there's a half in the front there. So, make some more writing space for myself here. So we have 1/2 g of 2 minus 1/2 g of 0. And using our table, I can find out what g of 2 is. G of 2 is 0, so I've got 1/2 times 0. And then g of 0 is 2. That just goes away. And 2 times 1/2 is 1. And then there's this negative in the front here. So that's -1 would be my final outcome there. Go ahead and take a look at one more. All right, so this time we have the integral of, our u. I think I'll write it up here so I have a little more space actually. So my u is going to be g of x, the inside function there. The derivative of u with respect to x is g prime of x, and dx is equal to du over g prime. So rewriting this then, we're going to have f double prime of u times g prime of x, and then replacing the dx, we have du over g prime of x, and these are going to cancel out. And once again, we want to change our limits of integration here, so the 2, plug it in there. G of 2 is 0. And then we'll plug in the 1. G of 1 is -1. And so rewriting this nice and neat, we have that. So the only thing that's really different about this problem happens now, and that's the fact that we have a double prime here. And when you integrate a double prime, it becomes a single prime. Okay, so after that, there's really not much new going on. We have f prime of 0 minus f prime of -1. And then we're just going to use our table to calculate the rest of it from there on out. Okay. So f prime of 0, that would be -3. F prime of -1, that would be -5. Got some double negatives here, so that's plus, and -3 plus 5 is 2. Final answer is 2. All right, guys, so those will be your FRQ type style questions there. So how will you be graded on these things? Well, the FRQs usually comprise about 20 to 25% of your test, but I'll tell you the things that we'll be looking for. First of all, did you do the U-substitution? In other words, did you replace this with U, and did you replace this with a DU and accurately cancel out the G or whatever, right? So that's one thing. Now, part of the U substitution, but I will be counting that as a separate point, is did you change the limits? Okay, so in other words, when you do U substitution, the limits change as well. So that's another thing we'll be looking out for there. Another thing is, did you do the integration correctly? So in other words, whenever you integrate f prime, you get f, right? Or if you integrate f double prime, then you get f prime. So did you do the integration correctly? And then the final thing I'll be looking for is just the final answer. So I'll be looking for 4 different things. Altogether, these parts on the FRQ will make up about 20% of the overall quiz score. So once again, we're looking for the U-sub, the change of the limits, the integration, and the final answer. Now, obviously, if you get the first part wrong, that's going to kill it for the rest because you can't really get the rest of it right. So you got to make sure that you really get the first things right, and that'll help you do better with the last parts. But anyway, there you guys have it, and we will see you guys in class. Bye-bye.